Greetings, class. Imagine, if you will, shrinking an entire massive football stadium all the way down to the microscopic size of a single atom. Now, if you were to wander right into the center of that atom-sized stadium, looking for its core, the nucleus, you know what you'd find? You'd be searching for something roughly the size of a tiny green pea, just resting right there on the 50-yard line. It's a completely mind-bending shift in perspective, isn't it?
Today, we will study elements and atoms. Consider our sun, which we often see beautifully captured in composites using X-ray and solar optical telescopes. The sun, much like everything else in the universe, is made largely of the elements hydrogen and helium. These fundamental building blocks, these atoms, literally make up every single piece of matter around us. Living, non-living, you name it. By the end of this lecture, you're going to understand exactly how these invisible components dictate the rules of our entire physical world.
Here's our syllabus for today's masterclass. We'll be covering Introduction to Elements, the structure of atoms, the vast empty space, subatomic deflection experiments, comparing subatomic particles, and finally, daily life and exam tips. Let's get right into it.
Section 1. Introduction to Elements. What is matter made of? Okay, let's dive straight into this. Pay really close attention to the rigorous academic precision of these definitions, because word-for-word accuracy is absolutely crucial for your exams. First up, a chemical element. This is a pure substance that cannot be chemically broken down into simpler substances. Essentially, this means an element contains only one kind of atom. Some of them, like gold or nitrogen, are just found on their own in nature, but most are combined into compounds. Right, so what's an atom then? An atom is formally defined as the smallest particle of an element capable of taking part in a chemical reaction. Now, to communicate globally, every single element has its own unique, internationally accepted chemical symbol. Notice how the first letter is always capitalized, and the second one, if there is one, is always lowercase. But check out these fascinating historical origins. While carbon is just a simple C from English, lithium's Li actually comes from the Greek word lithos, meaning stone. Iron is Fe from the Latin word ferrum. And potassium's K? That is a fantastic blend of history, deriving from the Arabic alqualia and the Latin collium. Pretty cool, right? Section 2. The structure of atoms inside the invisible.
So when we zoom in past the macroscopic element, this brilliantly illustrates what we actually find. When picturing a simple, highly useful model of a carbon atom, right there at the dead center is the dense nucleus containing the protons and neutrons. And surrounding that nucleus, zooming around its specific energy levels, are the electron shells, where the electrons live. Let's break these components down one by one, shall we?
First off, the nucleus and its nucleons. The nucleus is a very small yet extremely dense region right at the center of the atom, holding almost its entire mass. It houses two specific types of particles. We've got protons, which are positively charged. Now, this is crucial. The number of protons determines the absolute identity of the atom. For sure, hydrogen has 1, carbon has 6, oxygen has 8. If the number of protons changes, the element itself literally changes. We also have neutrons. These are electrically neutral, meaning zero charge, and their main job is to contribute to atomic mass and help stabilize that incredibly dense nucleus. Now, outside the nucleus, we find the electrons. These are negatively charged particles that rapidly occupy regions of space called electron shells, or energy levels, at very particular distances from the nucleus. In a perfectly neutral atom, the negative completely balances the positive, meaning the number of electrons exactly equals the number of protons. Think of electrons as the social butterflies of the atom. They're the ones that participate in bonding and chemical reactions. For instance, carbon has 6 electrons. That's 2 in the first shell, 4 in the second. That specific 4-electron outer shell allows it to form multiple bonds, which, frankly, forms the very basis of all organic chemistry and life itself.
Section 3. The vast empty space. Understanding atomic scale.
10 to the power of -10 meters. That microscopic, totally incomprehensible number is the approximate diameter of a single hydrogen atom. Its mass is equally tiny, weighing in at just 1.67 times 10 to the -27th kilograms. They're entirely invisible to the naked eye.
Now, what's really interesting about this concept is how it brings us back to our football stadium analogy from the start of class. If the entire atom is the stadium, that heavy, dense nucleus is literally just a small piece sitting right on the center mark. The electrons, they're even smaller than the protons and neutrons, just whizzing around way up in the outer stands. This means that despite having mass, most of an atom is actually empty space. I know, it's crazy. This vast spacing is precisely why, under certain conditions, tiny particles can pass straight through solid matter.
Section 4. Subatomic deflection experiments. How do we know this?
Okay, so you might be wondering, if atoms are invisible and mostly empty space, how on earth did scientists figure all this out in the first place? Well, they acted like detectives. Scientists deduced the electric charges of these subatomic particles by observing how beams of the particles behaved when passed through electric fields. Enter J.J. Thomson and his legendary cathode ray tube experiments. This was a real game changer because it fundamentally proved the existence of the negatively charged electron.
Let's actually walk through the exact step-by-step sequential operation of this brilliant experimental setup. Step 1. A metal wire, called the cathode, is heated to a really high temperature using a low voltage. Step 2. This intense heating causes electrons to be given off or emitted. Step 3. Because unlike charges attract, these newly freed electrons move rapidly toward positively charged metal plates. Step 4. A focused beam forms and travels right through the vacuum of the tube. And finally, Step 5. The beam strikes a fluorescent screen at the far end, producing a highly visible spot of light.
So, what happens when an electric field is applied across the tube? The beam behaves differently depending on the particle. Electron beams deflect, or bend, really easily toward the positive plates and away from the negative ones. This proved, without a doubt, they have a negative charge and an extremely small mass. Proton beams, on the other hand, deflect toward the negative plate, proving their positive charge. But here's the funny part. The sluggish, heavy proton needs a massive, high-voltage push just to bend its path, especially compared to the incredibly light and nimble electron. I mean, a proton is about 2,000 times heavier than an electron. Meanwhile, neutron beams. They don't bend at all, proving they are perfectly 100% neutral.
Section 5. Comparing subatomic particles. The master table. Let's move to and see how this builds into what I call the master table. Class, lock this into your memory right now. The proton, positive +1 charge, relative mass of 1, located in the nucleus. The neutron, neutral, 0 charge, relative mass of 1, also located in the nucleus. The electron, negative -1 charge, a relative mass of 1/2000, located out in the electron shells. You absolutely must commit this exact information to memory. It is a strictly tested, high-yield component in structured and multiple-choice A-level questions. Seriously, know it inside and out.
Section 6. Daily Life and Exam Tips. Practical Applications.
Now, why do we care about protons, neutrons, and electrons outside of a chemistry classroom? Well, because these incredibly tiny, mostly empty structures dictate absolutely everything in our daily lives. In medicine, specific radioisotopes are utilized for advanced medical imaging and cancer treatment. In electronics, the precise movement of those nimble, negatively charged electrons forms the basis of literally every electrical circuit, including the rechargeable lithium battery sitting in your phone right now. In chemistry, understanding the electron shell arrangement explains all bonding and chemical reactions. And in energy production, it's the manipulation of the protons and neutrons inside the nucleus that fuels nuclear power.
So, the crucial point is how you actually translate this knowledge to your exams. Do not confuse your terms. An element contains only one type of atom. An atom is the smallest reacting particle. The nucleus contains only the heavy protons and neutrons, while the electrons just buzz around in the shells. And listen, when you're asked to draw atoms in your exams, always draw carefully labeled diagrams. The mark schemes strictly award points for the correct number of particles, the proper shell arrangement, correct charges, and accurate scientific terminology. Don't leave easy points on the table. To summarize today's masterclass, matter is made of elements. Elements are made of atoms, and atoms are made of a dense nucleus surrounded by orbiting electrons in a vast expanse of empty space. We proved this through brilliant historical deflection experiments, and this microscopic structure governs our entire macroscopic world. But I want to leave you with a mystery to ponder until our next class. If atoms are indeed mostly empty space, if they are really just tiny peas inside massive stadiums, why don't objects pass right through one another when they collide? Why doesn't your hand pass right through the desk? Think about those electron shells, and I will see you next time in our next explainer session.
The screen presents essential keywords for this topic categorized by different exam boards. These terms need careful focus while studying as they are very important and should not be ignored at any cost. Moreover, past paper analysis for each board and paper type is also included. Pay close attention to this section as it will significantly strengthen your preparations. Also make an effort to understand how each keyword is used in the context instead of just memorizing them separately. Regular use of these terms in past paper practice will improve your accuracy and exam performance.
Please subscribe our channel to get more educational videos. Thank you.